This video is sponsored by Squarespace.
Today we're going to look at what is maybe one of the most famous exponential Diophantine equations, and maybe its fame comes from its history. So our final goal will be to find all natural numbers x and n such that x squared plus 7 is equal to 2 to the n. And a little bit about the history of this equation. So in 1913, Ramanujan conjectured that the only solutions occurred when n was 3, 4, 5, 7, or 15. And the corresponding values of x are 1, 3, 5, 11, and 181. Ramanujan didn't prove this though. The first proof of this came in 1943 by a Norwegian mathematician named Nagel. Just a little aside here, last year I was invited to a student-driven conference in Norway and I really enjoyed myself there. So anyone from that conference watching, thanks for inviting me, it was great. So our solution that we'll present, which I think is the most elementary solution, you can really get into the weeds of higher math here if you're not careful. So our solution is based on a 1987 paper of Wells-Johnson, although I found this approach in many different places. Okay, so how are we going to do this? Well, we're going to first notice that if n is equal to 1 or 2, then we clearly have no solution. And well, why is that? Well, the n equals 1 case would give us something like x squared equals -5. Well, that clearly doesn't have a solution inside of natural numbers. And then the n equals 2 case, well, that would give us something like x squared equals, well, let's see, we've got 4 minus 7, -3. So again, no solution there. Okay, so what does that mean? So that means all solutions occur when n is bigger than or equal to 3. And of course, like Ramanujan's conjecture covers that, although these first two cases are really trivial. So in fact, we do get a case when n is equal to 3. Maybe we'll look at that case just so that we have a feel for how this works. So notice with n equal 3, we have x squared plus 7 equals 2 cubed, but that's clearly equal to 8. And so we get x squared equals 1, which means x is equal to 1 because we're over positive integers. And then maybe let's jump up and look at the case when n is equal to 5. Skipping this case right here when n is equal to 4. And note when n is equal to 5, we'll get x squared plus 7 is equal to 2 to the 5, which is equal to 32. But in this case, we'll get x squared is equal to 25, which means x is equal to 5. So we've clearly got a solution right there as well. And now we'll move into the real meat of showing that the only solutions come from this list right here. And we are in fact going to work inside of what's called an extension of the integers. And what I mean by that is we're going to take the integers and maybe add to them some complex number. And how are we going to do that? So we'll work inside of this thing that I'll call z adjoin omega, which is everything of the form a plus b omega, where a and b come from integers. But you might say, well, what's omega? Well, omega is going to be equal to 1/2 times 1 plus the square root of -7. So this makes z adjoin omega like an imaginary ring of integers. But another thing that's important about this is that this structure right here has so-called unique factorization. And what I mean by it having unique factorization is, well, we've got some sort of theorem that allows us to factor any element of this into, well, what's essentially a prime. So we've got like a fundamental theorem of arithmetic for this structure right here. And we won't prove that this is a so-called unique factorization domain or a UFD, but we will use that fact. And now I'm going to make a couple of quick observations about omega. And this will help us like with the structure of our calculation later. So let's notice if we do omega plus omega bar, where omega bar is simply the complex conjugate. So it's going to be 1/2 minus or times 1 minus the square root of 7. So there's our little omega bar. So if we add omega and omega bar, we get the number 1. Because notice the imaginary parts cancel. And then if we do omega times omega bar, well, you can check that the 1/2 times 1/2 is 1/4. And then we've got a difference of squares situation happening right here. So we'll have 1 squared minus root negative 7 squared, but that ends up being 1 plus 7 or 8. So we have 8 over 4 or the number 2. So we've got that kind of setup right there. But now this gives us a quick way to find the quadratic equation satisfied by omega and omega bar. So let's look at t minus omega times t minus omega bar. Multiplying that out, we'll have t squared minus omega plus omega bar times t plus omega times omega bar. That's just from distributing everything. But note that that means that we get t squared minus t plus 2, just by these calculations over here. So that means omega and omega bar satisfy this polynomial being equal to 0. So in other words, we know that omega squared is equal to omega minus 2, which we get just from solving this for t squared and then plugging in omega. Okay, so let's take some of this information and see where we can go.
Before we continue, I'd like to thank today's sponsor, Squarespace. Are you ready to reimagine your online presence? Look no further than Squarespace. Squarespace is a service that takes the hassle out of creating a website and will better represent you and your brand. Choose from a vast library of professionally designed templates that are not only visually stunning, but also fully customizable to reflect your unique style. The new Fluid engine gives you complete control over the structure of your website. Squarespace's intuitive drag-and-drop builder allows you to create and edit your website effortlessly. No technical skills required. Every website you create with Squarespace is fully optimized for mobile, so your audience can enjoy your content on any device, anywhere, anytime. Use Squarespace's analytics to measure your website's performance and make informed decisions for growth. I use Squarespace for my website and find it easy to use with plenty of integrations. They even have a plugin for LaTeX. It allows me to include equations on my website very easily. Whether you need a place to sell your merch or show your art, Squarespace has the tools that you need to keep your website modern and easy to use. Give Squarespace a try today, and when you're ready to launch, go to squarespace.com/MichaelPenn to save 10% off your first purchase of a website or a domain using code MichaelPenn. Thanks again to Squarespace for sponsoring today's video.
Okay, so we're working with this number omega that satisfies these rules up here. But let's now take this number root negative 7 and solve it in terms of omega and omega bar. Or I guess I should say express it in terms of omega and omega bar. So let's note that root negative 7, well, that's going to be equal to 2 times 1/2 times 1 plus root negative 7. So I've got the 2 there because I want to cancel out this half. And I've got this whole thing here because that is our omega. But notice now I've added a 1, so I need to subtract 1 there. And now let's use the fact that all of this stuff that I'm underlining in red is our number omega. So that gives us 2 times omega minus 1. And then similarly, we have the square root of negative 7, or negative the square root of negative 7 is equal to 2 times omega bar minus 1. So you can check that pretty similarly. So now notice that if we take our equation, 2 to the n equals x squared plus 7, we can factor it as x plus root negative 7 times x minus root negative 7. And then we can take those square roots of negative 7 and express them in terms of omega. So let's do that. So here we've got this as x plus 2 omega minus 1, so that's our root negative 7. And then we have x plus 2 omega bar minus 1. That's our root -7 with the minus sign in front. And now from here, I'll factor a 2 out of each of these. That'll give me something like this. Well, 2 times 2 is 4 because we're taking 1 out of each. We'll have x over 2 and minus 1 over 2 because we factored a 2 out, leaving us with x minus 1 over 2 plus omega. And then likewise, the next term will be x minus 1 over 2 plus omega bar. And now I'd like to make the following observation. And I'm going to write it down first and then we'll talk our way through it. So I'm going to say y, which is equal to x minus 1 over 2, is in fact an integer right here. And how do we know that? Well, let's go back to our original equation over here. We know the solution to this only occurs when n is bigger than or equal to 3, so the right-hand side is even. That means the left-hand side has to be even. 7 is odd. That means x squared also has to be odd, which means x has to be odd. But if x is odd, x minus 1 is even, and thus x minus 1 over 2 is an integer. So that means we can work with this x minus 1 over 2 without getting outside of the integers. Okay, so now let's step back and look at the equation we have produced. We have 2 to the n is equal to this thing right here. Well, I might as well divide both sides by 4, leaving me a 2 to the n minus 2 over here, and then replace my x minus 1 over 2 with y. So now we've got this new equation, y plus omega times y plus omega bar equals 2 to the n minus 2. And this is an equivalent equation to our maybe original Diophantine equation over here. But now it's occurring within this like extension of the integers. Okay, let's see what we can do with this. Okay, so this is where we've gotten so far. Now we're going to do a couple of more little calculations. Next up, we're going to use the fact that omega times omega bar is equal to 2. So that means 2 to the n minus 2 is the same thing as omega to the n minus 2 times omega bar to the n minus 2. But then y is an integer, which means y bar is also an integer, which means that we can take this bar, this conjugation, and pull it out maybe over this whole term. So now we have y plus omega times y plus omega all bar is equal to omega to the n minus 2 times omega bar to the n minus 2. So we've got an equation that looks like this. But note here what we've done is we factored 2 to the n minus 2 into irreducibles. So I won't check this, but omega and omega bar are so-called like irreducibles or primes within this z adjoin omega. So let's write that down. So omega and omega bar inside of z adjoin omega are prime. Okay, but then that means that one of these factors over here has to be either all of the omegas or all of the omega bars and vice versa. And that's because these two objects don't share any common factors, and then these two objects, well, they're prime, so they don't share any common factors. So we're skipping a couple of little steps here, but it essentially breaks down into we're just dealing with primes in this really fancy setup. And now we're going to look at this factorization and see which term on the left is gobbling up this omega to the n minus 2 term. So it could either be this or this. Well, maybe not exactly those, but those up to multiplication by invertible elements, but the only invertible elements inside of z adjoin omega are plus minus 1. Another thing that we won't really prove, but isn't too hard to prove. So that sets us up the two possibilities. So we have omega or y plus omega is equal to plus minus omega to the n minus 2, or y plus omega bar is equal to omega to the n minus 2. I guess I needed a plus minus omega to the n minus 2. But now let's notice that this number y here is an integer, like a pure integer. So that means when we look at the coefficient of integers and the coefficient of omegas, well, the coefficient of omega here is just 1 over here on the left-hand side. So in other words, we have omega to the n minus 2 is equal to a plus minus omega, where here a is just an integer. So let's reiterate what we did over here. We took this left-hand side and maybe forgot its fine structure. We just thought about its real part and its like omega part. And its real part is made up by this number a, and then its omega part, well, it's left over, but it's totally contributed by this omega, which after moving the pluses and minuses over is either plus minus 1. And then we can make a pretty similar argument right here. So let's notice that this omega bar can be rewritten as 1 minus omega. But then doing the same kind of thing, we notice that the only contributor to the coefficient of omega over here is from that minus sign right there. It doesn't build up to a larger number. So that means that in this case as well, it condenses down to this expression here. Okay, so what do we have? Well, what we have is omega to the n minus 2 has to be able to be written as a number a plus minus omega. So in other words, the coefficient of omega is 1. And this is in the cases when n gave us a solution to our original equation. This is not always. This is in the cases that come from our solutions. So that's important to notice as well. Okay, so let's start with the summary of that at the top of the next board and then do some more calculations. So let's see where we are so far. We determined that if n was a solution to x squared plus 7 equals 2 to the n, in other words, our original Diophantine equation, then omega to the n minus 2 was equal to an integer, which I've called a, plus minus omega. Okay, so now let's see where we can go from there. So what I'll do now is define two linked sequences of numbers. And those will be called a sub n and b sub n. They'll be integers, and they'll be defined by the expansion of omega to the n. And now here's where it gets a little bit unnerving, but I think it's okay. And I think this is really the best way to do it. So there's nothing to do here. And that is that this power of omega here that we'll be looking at is 2 less than the one that will give us a solution based off of this rule up here. So as you'll see, our final solutions here for this value then will be 2 less than all of these numbers, but we just have to do that translation here. Okay, so back to this. We're defining an and bn by omega to the n equals a sub n plus b sub n times omega. Okay, nice. And that's possible because of, well, I don't have it on the board, but that rule where omega squared equals omega minus 2. So that allows you to take any power of omega larger than or equal to 2 and write it as a power that is 1. And now we want to do this nice trick. And that trick is to take this definition of omega, or this definition of an and bn, which is the expansion of omega to the n, and maybe turn it into a recursion for a sub n and b sub n. And how are we going to do that? Well, let's notice that omega to the n is the same thing as omega times omega to the n minus 1. I think that's pretty clear. But then that's going to be the same thing as omega times an minus 1 plus bn minus 1 times omega. Just by the way that we're defining our a sub n and our b sub n. Okay, but then over here, this omega to the n is an plus bn omega. Okay, now what can we do from there? Well, let's take this left-hand side and we'll distribute the omega through and then apply maybe some of the defining rules of omega. So that means we have a sub n minus 1 times omega plus b sub n minus 1 times omega squared. Using the fact that omega squares to omega minus 2, we can collect some terms here. And what we'll see is this. We have negative 2 times b sub n minus 1, and then plus a sub n minus 1 plus b sub n minus 1 times omega. But that was all our calculation over here on the left-hand side. But that has to be equal to the right-hand side. So that's equal to an plus bn omega. But now we can compare the non-omega part and the omega part, and we'll get this nice recursion for our an and our bn terms. And this is like a linked recursion. So the red stuff is equal, and then the blue stuff is equal. So in other words, we'll have a sub n is equal to minus 2 bn minus 1, and we'll have bn is equal to an minus 1 plus bn minus 1. And then you might say, well, what about our seeds here? And you can easily calculate the seeds by looking at omega to the 0 or omega to the 1. Maybe let's look at omega to the 0, which is equal to 1, which is equal to 1 plus 0 times omega. So what does that tell us? That tells us that a sub 0 is 1 and b sub 0 is 0. So those are our two seeds. And then let's step back again and note that our goal is for this b sub n term to be equal to plus minus 1. So this is what we want. We want this to be equal to plus minus 1 because that'll give us a solution. So now we could make a chart of these b sub n terms and check out when they're plus minus 1. And what we'll see is that we get the b sub n is plus minus 1 for n equals 1, 2, 3, 5, or 13. And those are going to correspond over here to our original solutions of 3, 4, 5, 7, and 15 because of this translation by 2 built into our construction. Okay, so what do we want to do? Well, we want to classify all values of n so that b sub n is equal to plus minus 1, and thus that will give us all values of n that lead to a solution to our maybe original Diophantine equation. So let's get to that. Okay, using our two sequences here, what we've come up with is that the b part of this sequence is equal to plus minus 1 if and only if n plus 2 gives us a solution to our original Diophantine equation. So technically we've only done one direction of this if and only if statement, but the other direction is fairly straightforward and definitely a lot easier than the calculations that we've done and the calculations that we will do. Okay, so now what we'll do is classify all of the values of n that make this occur. And if we can classify all the values of n that make that occur, then we have all the values of n that make this equation solvable. And hopefully it'll be the same list that Ramanujan conjectured and people proved in the end. Okay, so let's get to it. So we're gonna note that we can write omega in the following way. First, using the fact that omega plus omega bar is 1, we can write it as 1 minus omega bar. I think that's pretty clear. But then let's notice that this is equal to b2 minus b1 times omega. So maybe keeping in mind that chart that we showed with values of b will be helpful because we'll use the values of b from time to time, but I can't keep them on the board the whole time. Okay, but this kind of gives us some motivation that perhaps there's a nice formula for powers of omega in terms of, well, this expression involving b's. And in fact, there is. And you can prove that via induction. And just for time, a lot of these steps that can be proved like fairly easily with induction, we're gonna skip. Okay, so with induction, we can prove that omega to the n power is equal to b sub n plus 1 minus b sub n times omega. Well, notice that follows this pattern that we've observed in the orange underlining stuff. And then really similarly to that, we can get the following expression. Well, actually, just by taking the complex conjugate here. So omega bar to the n is equal to bn plus 1 minus bn omega bar, given that the b's are integers. Okay, but now we can take those two equations and subtract them, and we get this nice expression. We get omega n minus omega bar to the n is equal to, oh, notice that the b sub n plus 1's cancel. That's maybe our motivation for subtracting those, just to get maybe those bn plus 1 terms out of there. And we'll be left with b sub n omega bar minus omega. But this is like pretty quickly solvable for b sub n, and we've got this nice expression for b sub n only in terms of omega. And what is that going to be? It'll be omega to the n minus omega bar to the n over omega bar minus omega. But now let's see where we're going to go from there. And I'm going to like erase my heading just for space. So maybe refer back to this heading if you need to as we go on with the upcoming steps. So these were our two equations that we left on the last board. There was a slight typo on one. Here we should have omega to the n equals b sub n plus 1 minus b sub n omega bar. So that's important. Now what I'd like to do is look at the following object, and that will be omega to the n times k plus 1. And I want to think about this as omega times omega to the n raised to the k power. But then I can think about that as omega times, well, my omega to the n can be expressed as this. So I've got omega times b sub n plus 1 minus b sub n omega bar to the k power. Okay, so next up what I'll do is I'll expand that using binomial expansion and, well, multiply the omega through. And then simultaneously, I'm going to pull the first two terms out. So that'll give me something like this. I have omega n k plus 1 will be equal to b sub n plus 1 raised to the k times omega. And then my next thing will be minus 2k bn plus 1 to the k minus 1 times b sub n. So that's my like second term for my expansion, or my zeroth and my first term, after multiplying through by omega here. And then next up I'll have plus the sum as j goes from 2 to k, minus 1 to the j, and then we have k choose j. So this is going to be everything that remains after the zeroth and the first term. So here we have bn plus 1 raised to the k minus j. We have bn raised to the k. And then finally we have omega bar raised to the j minus 1. Now we're going to take this equation and look at its conjugated version. And so that'll be like omega bar to the nk plus 1. And here we're just going to go through every term here and we'll conjugate it if necessary. You know, this is just an integer, so its conjugate is itself. So that's going to turn into omega bar. This thing is going to stay the same, so b sub n. And then every term in here will get barred. So here we have minus 1 to the j, k choose j, bn plus 1, k minus j, bn k, and then we'll have omega to the j minus 1. Because if you bar something that's been conjugated, well, that just goes back to the original, if you will. Okay, so next up what I'll do is I'll take these two expressions and I'll subtract them. And as I subtract them, I'll apply this rule right here. So notice here I'll have omega to the nk plus 1 minus omega bar to the nk plus 1. So that'll end up giving me something like b sub nk plus 1 times this object right here, kind of depending on the order of subtraction. Okay. So here, like I said, we'll have omega minus omega bar times b n k plus 1, where we choose the order of subtraction to make it like that. And then here we'll have omega minus omega bar times bn plus 1 to the k from this bit. Those two bits are real, or they're just integral, so those are going to cancel. And then over here we'll have this sum. J goes from 1 up to k minus 1 to the j, k choose j, bn plus 1 to the k minus j, bn to the k, and then that difference introduces another one of the b's. And it's going to be b sub j minus 1 times omega minus omega bar. So we've got this nice expression right here. Oh, but now look at this. We've got this factor of omega minus omega bar everywhere, so we can divide that out. And then we've left with an equation that only involves integers. So let's see what we can do with that equation. So in the last board, we ended up with the following equation that involves the b's occurring within the integers. And next up, we want to go back to that chart of the values of our sequence b sub n and reduce it mod 16. And we'll notice that if we reduce it mod 16, we have bn is congruent to 1 mod 16 if and only if n is equal to 1 or 2. And that's because after the case when n is equal to 1 or 2, we have a periodic sequence with period 4. And then you'll see, because we have a period of 4, the only way that bn could be -1 is if it's -1 mod 16, and that only occurs at numbers that are 1 mod 4. So putting that all together, we can maybe set n here equal to 4, because those are going to be the only values of n that indeed would lead us to a solution. So let's do that. Let's set n equal to 4 here and see what we get. So we'll have b sub 4k plus 1 equals b sub 5 squared minus 2b sub 4 squared. And then we've got this sum here. J is going from 2 up to k minus 1 to the j. And then we have k choose j. We have b5 k minus j, b4 j minus 2, and then bj minus 1. We have a known solution at b sub 13, which is the case when k is equal to 3. So that means we might as well assume that k is bigger than or equal to 5. And we can say that k is bigger than or equal to 5 and not k is bigger than or equal to 4, because if you reduce this thing mod 3, you'll see that k has to be odd. But now for our next step, since we know what b5 and b4 are, we can put those inside of this equation. And that, along with the fact that we're going for a solution, so we know that this b4k minus 1 is equal to -1, will allow us to rewrite this whole thing in the following way. So it turns into the following nice equation. And that is the sum as j goes from 2 to k of -1 to the j. And then we have k choose j. And then 3 to the j minus 1. And then b sub j minus 1 is equal to 0. So again, that's from plugging in the values of b4 and b5, and then using the fact that we know that b4k plus 1 is -1, given the fact that that gives us one of our solutions. Okay, so the next step is to divide by k times k minus 1, and we'll simultaneously pull out the first two terms of this sum. So let's see, that's going to give us a half minus k minus 2 over 2, and then plus, as j goes from 4 up to k, of -1 to the j. This is now k minus 2, choose j minus 2 by some binomial coefficient identities, and then 3 to the j minus 2 over j times j minus 1, again because of those binomial coefficient identities, and then bj minus 1 equals 0. So just to reiterate, that's from dividing by k times k minus 1 and pulling out the first two terms. But now let's notice that this big chunk right here is a rational number where the numerator is a multiple of 3. Okay, but then that means what's left over here also has to be a rational number where the numerator is a multiple of 3. But those two combine together to give us 3 minus k over 2. So 3 minus k over 2 needs to be something with a numerator involving 3. Oh, but that means that 3 minus k is a multiple of 3, which means that k is a multiple of 3. So in other words, 3 divides k. But then if 3 divides k, we can replace the k right here with a 3k and have this new expression involving b sub 12k plus 1. So let's get that expression on the board. So after that replacement, this is our new equation. And now, well, we have some other specific values of the b sequence built into this. And let's just use the fact here that b sub 12 is equal to 45 and b sub 13 is equal to -1. So that means that, well, we can put those numbers in and then again divide by this k times k minus 1, move some things around, and what we'll see is that we've got this equation where we have half plus the sum as j goes from 3 up to k. There we pulled out the first term. Well, we've got this binomial coefficient times 45 to the j minus 2 from that b sub 12 over j times j minus 1. And then we know that times b sub j minus 1 must be equal to 0. Okay, but now let's notice that we can play a pretty similar game to what we did before. Now, all the numerators here are multiples of 5. In other words, that if you put this together, this looks like a fraction where after reduced, you've got a multiple of 5 in the numerator. Oh, but notice that this thing, a half, does not have a multiple of 5 in the numerator. But that brought us to our contradiction. And what did that contradict? Well, that contradicted any values of the b sequence being equal to plus or minus 1 outside of the ones that gave us a solution to our equation. Which means that these are indeed the only solutions to our original Diophantine equation. And that's a good place to stop.